Hello, my name is Syifa Kamilah Qudsi, from Universitas Islam Negeri WALISONGO. Welcome to my project, Coupled Pendulum Dynamics, an experimental analysis using Lagrangian mechanics. Coupled pendulum systems are a classic example in classical mechanics, showing how two oscillating bodies can influence each other's motion through a shared connection. In this video, we will build a simple coupled pendulum apparatus from scratch, and use it to explore these dynamics through the lens of Lagrangian mechanics, a powerful mathematical approach for analyzing systems in motion. Building a coupled pendulum system requires just a few simple materials. Let's take a look at everything we'll need, and how each one maps onto a term in the Lagrangian mechanics we'll derive later. Next, cardboard, which serves as our rigid rod. Its mass and length will later define the moment of inertia used in the rotational kinetic energy term of our Lagrangian. First, a pair of scissors, our main tool for cutting and trimming materials like cardboard, and making precise adjustments to fit the exact size we need. A paper clip serves as the pivot hook, giving the rod a fixed point to rotate around. This pivot is the origin of our angular coordinate, theta. And finally, a rubber band, which acts as our spring. It stores elastic potential energy defined by the spring constant K, the same K that appears directly in our potential energy equation. This thread functions as our massless, inextensible connector, linking the elastic band to the load. That's why we treat it as a simple length constraint, rather than adding its own energy terms. This bolt acts as our point mass em. Its position along the rod, described by the coordinate x, determines both its kinetic energy and its gravitational and elastic potential energy. Double-sided tape acts as a strong adhesive, allowing us to firmly join and secure the cardboard pieces and other components together. With all our materials ready, it's time to bring them together. As we attach the pivot, the rod, and the elastic connector, we're physically building the two-degree of freedom system described by our generalized coordinates, theta and x. Here is our finished coupled pendulum apparatus. Let's see it in action and observe the coupled oscillation between the rod's rotation and the mass's translation, exactly the dynamics we'll formalize using the Lagrangian. This system oscillates through two coupled motions that continuously influence one another, the rotational motion of the rod, described by the angle theta, and the translational motion of the elastic stretch, described by the displacement x. Before deriving the equations of motion, we identify the constraints of the system. The pivot point is fixed in space, the rod behaves as a rigid body, and the connecting string is inextensible. Together, these give us a total of 4 constraints. Starting from 8 raw coordinates for the rod and point mass in 2 dimensions, and applying our 4 constraints, we are left with just 2 generalized coordinates, theta and x. This means the system has 2 degrees of freedom. Next, we calculate the total kinetic energy of the system. The rotating rod contributes a rotational kinetic energy term, while the oscillating mass contributes both a translational and a rotational component, since it moves along the rod as the rod swings. We then calculate the potential energy. This includes the gravitational potential energy of both the rod and the mass, and the elastic potential energy stored in the stretched band, based on its spring constant. This elastic behavior follows Hooke's law. The restoring force is proportional to how far the band is stretched, described by the spring constant K. As the load moves, this restoring force continuously pulls it back toward equilibrium, which is exactly the elastic term we included in our potential energy. Combining these, the Lagrangian of the system is defined as the total kinetic energy minus the total potential energy. This single expression contains all the information needed to describe the system's motion. Applying the Euler-Lagrange equation to the coordinate x gives us the equation of motion for the elastic displacement, showing how it responds to gravity, the rod's rotation, and the restoring force of the elastic band. Applying the same method to the coordinate theta gives us the equation of motion for the rod's swinging angle, showing how its rotation is affected by the changing position of the coupled mass along its length. To evaluate its structural integrity, we gently oscillate the apparatus and observe it from several angles. Consistent, repeatable motion here supports the validity of the equations of motion we derived earlier. That concludes this demonstration of coupled pendulum dynamics through Lagrangian mechanics. Even a simple system built from everyday materials, like cardboard, rubber bands, and thread, can reveal deep physical principles connecting rotational and translational motion. Thank you for watching, and I hope this project inspires further exploration into classical mechanics.